Hello and welcome back to Curiosity Lounge. Before we start, hit that red subscribe button so that you never miss out on any of our videos. For the first time in human history, a spacecraft, the Parker Solar Probe, has flown through the atmosphere of the Sun, sweeping through the superheated particles of the corona, a momentous moment that has provided scientists vital information on the nature of our closest star. The Sun's atmosphere, much like our own atmosphere, is composed of layers. Where we have the troposphere, stratosphere, and mesosphere, the Sun has the photosphere, the chromosphere, and the corona. We have a saying, hotter than the surface of the Sun. But the surface of the Sun, this photosphere, is not actually that hot. It ranges from about 6,200 degrees Celsius at the bottom and 3,700 degrees Celsius at the top. That's about the same temperature as a welding arc, and the air around the lightning bolt can reach temperatures 5 times hotter than the photosphere. What's weird is that the outermost layer of the Sun's atmosphere, the corona, is much hotter than the photosphere. The corona, starting about 2,100 kilometers above the surface of the Sun, reaches 500,000 degrees Celsius, 80 times higher than the surface. That's like walking away from a fire and the temperature getting warmer as you get further away from it. This is a strange anomaly that makes the Parker Solar Probe's achievement even more impressive, since at first glance, it's easy to dismiss that the probe only flew through the upper atmosphere, when in reality the upper atmosphere is vastly hotter than the surface. The reason this occurs is one of the many unsolved mysteries of the universe, and as such, is one of the primary missions of Parker Solar Probe. To gather information on the magnetic fields and charged particles in this region, and attempt to answer this riddle. To understand the achievement of the Parker Solar Probe, let's dive into the engineering and physics of its solar mission. The first big problem facing the Parker Solar Probe is actually reaching the Sun. Despite the Sun's gravity acting as an anchor for our entire solar system, getting close to it is not easy. In order to bring a satellite out of orbit around the Earth, we have to shed its angular momentum so that it falls back to Earth. The same has to be done when trying to bring something out of orbit around the Sun, except in this case, we are located 150 million kilometers from the Sun and traveling at 30 kilometers per second. And anything launching from Earth will be imbued with the same orbital velocity around the Sun. This means in order to achieve a tighter orbit to the Sun, we need to lower the spacecraft's orbital velocity around the Sun, and this is an incredibly energy-intensive task, especially when you add the energy needed to escape Earth's gravity. So let's say we want to first get our satellite from the Earth's surface into orbit around Earth. This will require us to accelerate our satellite by around 9.2 kilometers per second relative to Earth's surface. The satellite is now in orbit around Earth and traveling with it at 30 kilometers per second around the Sun. From here, we need to perform something called a Hohmann transfer. This is an orbital maneuver where we either change the spacecraft's orbital energy to adjust its perihelion, its closest approach to the Sun, or its aphelion, its furthest approach from the Sun. To visit an outer planet like Mars, we want to increase our aphelion by adding to the spacecraft's orbital energy, while reaching an inner planet requires us to reduce our perihelion by decreasing our orbital energy. To reach Mars from Earth's orbit requires a delta 5 of around 2.9 kilometers per second. Reaching Venus requires around 2.5 kilometers per second. This is found using the equation where mu, this Greek letter that looks like U, is the planetary parameter of the Sun, which is a product of the Sun's mass. R1 is the orbital radius we are starting from, in this case, Earth's distance from the Sun at 150 million kilometers, and R2 is the desired perihelion or aphelion. If we calculate the delta 5 required to reach the Solar Parker Probe's closest approach of 6.2 million kilometers, this would require a delta 5 of 21.4, over 8.5 times greater than the delta 5 required to reach Venus. That's an incredibly high delta 5, one beyond the capabilities of any rocket ever made. But on December 8, 2018, the Parker Space Probe launched from Cape Canaveral aboard the Delta IV Heavy, the world's second highest capacity rocket in the world, second only to the Falcon Heavy. To give the probe an extra push, the Delta IV was fitted with a special solid rocket third stage, providing an additional 3 kilometers per second of Delta V for the typically two-staged rocket design. Yet, even with this added power, the probe would never have gotten close to the Sun. To achieve its record-breaking flight, 1/7 that of the previous record holder of Helios 2, the Parker Solar Probe completed an astounding 5 gravity assists by Venus, with an additional 2 flybys due in 2023 and 2024. This number of flybys was needed because Venus is a relatively low-mass planet. The magnitude of velocity change a planet can provide is largely determined by its gravity, determined by its mass. In fact, the original plan for the probe was to do a single planetary assist by Jupiter, which would have brought the probe 3 times closer to the Sun, but this trajectory came with some issues. Because Jupiter's orbit is so much further from the Sun, the sunlight reaching the panels at its aphelion would have been 25 times dimmer, requiring much larger solar panels to power the spacecraft. This poses an issue when the spacecraft makes its way around Jupiter and begins to accelerate towards the Sun. The heat of the Sun would destroy the solar panels, and at this size they could not retract and hide behind the sun shield. Other options were available. A radioisotope thermal generator could have been used, but would have driven the cost, weight, and complexity of the spacecraft up significantly. The real selling point for this radical new flight trajectory was the added time and data it would provide scientists to fulfill the probe's mission to study the Sun. With the original Jupiter plan, the probe would have had just 100 hours inside the desired zone around the Sun, completing just 2 solar passes before the probe reached the end of its 8-year mission duration. While the new lower orbit plan would mean the Parker Solar Probe would take less than 150 days to complete its orbit around the Sun, allowing scientists to gather over 900 hours worth of data over the probe's 24 orbits around the Sun. That's all the time we have to explore the insane engineering of the Parker Solar Probe. If you enjoyed our video and learned something new, make sure to hit that like button and subscribe to our channel so that you never miss any amazing videos from us.